So hello students, today we are going to start with the next topic after the condensers, that is the Dalton's law of partial pressure. And also today in this lecture we are going to cover the turbines, the classification of turbines, their applications, their advantages, disadvantages and all that. Okay, so let's start with the Dalton's law of partial pressure. So see this pic, this is the inventor of Dalton's law. That is, Dalton's law is given by this person, John Dalton. Okay. So Dalton's law of partial pressure. As per this law, the total pressure in a container is the sum of the pressure each gas would exert if it were alone in the container. That means the total pressure is the sum of the partial pressures of the individual gases. Like if we say about the condenser, in the condenser there is a steam coming from the turbine. Okay, and along with that steam, some air also enters into the condenser shell. So what is in the condenser shell? That is the mixture of steam and air. So as per the condenser theory, the total pressure inside the condenser shell is equal to the sum of the steam pressure plus that is the sum of the air pressure. So that is the pressure, total pressure inside the condenser shell. Okay, because we have to apply this Dalton's law in our power plant engineering. So in case of our subject, we have to give the examples as per the power plant machinery. So we are taking here the example of condensers. So Dalton's law for the condensers especially. So see here the pic. This is the pic for the Dalton's law. See, this is one container containing some molecules of hydrogen, and there is one another container, some molecules of helium, and this is the total pressure. Okay, see here the pressure is written in terms of numerical value. Here it is 2.9 atmosphere and here it is 7.2 atmosphere. And the total pressure as per the Dalton's law theory, that is the sum of the individual pressures, that is 2.9 plus 7.2. So this one gives you the 10.1 atmosphere. If the both the gases are mixed together, then as per the Dalton's law, it is the sum of the individual pressures. So that is the Dalton's law. So the Dalton's law of partial pressure, the total pressure exerted by the mixture of gases or a mixture of gas and vapors which have no chemical action on each other, that means that are not chemically reacted with each other, they are separated, is equal to the sum of the partial pressures of the constituents of the mixture if it occupied the volume of the mixture at the temperature of the mixture. So this is the definition for the Dalton's law of partial pressure. And so the total pressure in the condenser, now we have to deal this Dalton's law with respect to the condenser theory, that what is there in the condenser shell or what is the pressure inside the condenser shell. Okay, so the total pressure in the condenser is the sum of the partial pressure of steam and air. Okay, because in the condenser cell there is a mixture of steam and air. Okay, that is coming from the boilers, from the turbines into the condenser. So the pressure of this mixture, which mixture? Steam and air, is equal to the partial pressure of steam plus the partial pressure of air. So according to the Dalton's law, so mathematically this can be written like this, that is PC, that is total pressure in the condenser. This is equal to PS plus PA, that is the partial pressure of steam and partial pressure of air. So this is the Dalton's law. And see here, there's another figure, steam plus air, that is in the condenser, pressure in the condenser, that is a mixture of steam and air. And this is equal to the sum of these two pressures, that is the pressure of steam and pressure of air. So this is about the Dalton's law. Now next is the various sources of air leakage in the condensers. The following are the main sources through which the air may enter into the condenser. Then that means how the air comes into the condenser. Because in the condenser, we have to feed only the steam that is coming from the turbines, but air also comes along with that steam. So the dissolved air in the feed water enters into the boiler, which in turn enters into the condenser with the exhaust. Okay, so from the boiler, indirectly the air enters into the condenser. The air leaks into the condenser through various joints due to high vacuum pressure in the condenser. So there may be some leakage of air from the condenser through the joints. Okay, because inside the condenser, the pressure is very high and which pushes the air out through that joints. In case of jet condensers, the dissolved air with the injection of water enters into the condenser. Okay, because we know that in case of jet condensers, the cooling water and steam comes in direct contact with each other. And with that, some air also enters into the condenser shell. So these are the various sources of air leakage. And what are the effects of that air leakage? So it reduces the vacuum pressure in the condenser. First, the vacuum pressure inside the condenser shell reduces with that air. Since air is poor heat conductor, particularly at low densities, so it reduces the rate of heat transmission. So this is another effect of air leakage. It reduces the rate of a heat transmission. What heat transmission? That means the effect of cooling down of steam into the water, into the condensate. Okay. Also, third point, it requires large air pump. If there is more air into the condenser shell, so large air pump is required to remove that air, to extract that air from the condenser shell. So moreover, an increased power is required to drive the pump. Okay, so these are the various effects of air leakage into the condenser shell. Now, next, there are some terms, mathematical terms to calculate efficiency formulas. So first one is the condenser efficiency. So the condenser efficiency is defined as the ratio of temperature rise of cooling water to the vacuum temperature minus inlet cooling water temperature. Okay, so this is the condenser efficiency, and this is equal to the temperature rise of cooling water. What is the temperature rise? That means the cooling water that we directly get from some river is at low temperature. Say about the cooling water is at maybe at 10 degrees C or at 15 degrees C. Okay, but when this cooling water comes in contact with the steam that is coming from the turbine, its temperature increases. Okay, so there is change in the temperature of cooling water, that is change in the inlet temperature of cooling water and outlet temperature of the cooling water. Okay, inlet temperature, that is directly taken from the river. Outlet temperature of cooling water, that is when it comes in contact with the steam. So its temperature increases to 40 degrees C or 45 degrees C or maybe more. Okay, so that is the temperature rise of cooling water. And vacuum temperature minus inlet cooling water temperature, that is inlet cooling water temperature that is taken from some river. So mathematically it is condenser efficiency, it is equal to TO minus TI. TO is the outlet temperature of cooling water. That outlet, that means the cooling water after it mixed with the steam, after it comes in contact with the steam. And the inlet temperature of cooling water, that is directly when taken from some river or lake. Okay, and TV is the vacuum temperature in the condenser shell. Okay, so this is a formula for the condenser efficiency. And next, vacuum efficiency. that how much the vacuum is created in the condenser shell. The minimum absolute pressure, which is also called as ideal pressure, at the steam inlet of a condenser is the pressure corresponding to the temperature of the condensed steam. Okay, so what is the minimum absolute pressure? That is the pressure related to the inlet steam of the condenser. So the pressure of the steam that is at the inlet level of in the condenser. Okay, the corresponding vacuum called ideal vacuum. So this is called as ideal pressure and this is called as ideal vacuum, is the maximum vacuum that can be obtained in a condensing plant with no air present at that temperature. Okay, that is the ideal vacuum when no air is there in the condenser shell. Okay, but we know कि losses are there always. Okay, so as the air is there, so ideal conditions is very difficult to achieve. So, but the ideal vacuum is that when no air is present in the condensing plant. So that is the ideal vacuum. The pressure in the actual condenser is greater than the ideal pressure by an amount equal to the pressure of the air present in the condenser. So, but what is the condition inside the condenser shell? That inside the condenser shell, there is the actual pressure. Okay, and that actual pressure is due to the pressure of air present in the condenser, which is always greater than the ideal pressure, because I've already said that it's very difficult to get the ideal condition because air is always there in the condenser shell. There are always chances of air inlet into the condenser shell. Okay, so the actual pressure in the condenser shell is always greater than the ideal pressure. And how much greater than the ideal pressure? That is equal to the pressure of the air present in the condenser. So that is the actual pressure. So what is the actual pressure? That is equal to the ideal pressure plus the air pressure. Okay, that is the actual pressure. So the ratio of actual vacuum, this one, actual vacuum, no, this one is the ideal vacuum. The ratio of the actual vacuum to the ideal vacuum is called as the vacuum efficiency. Okay. So mathematically, it can be written like this: actual vacuum divided by ideal vacuum. And what is the actual vacuum? That is equal to the barometric pressure. So barometer is a device to works equivalent to the atmospheric pressure. Okay, barometric pressure minus actual pressure. Okay, and ideal vacuum is equal to barometric pressure minus ideal pressure. Okay, ideal pressure, as we know that it is always less than the actual pressure. So you have to calculate the actual vacuum using this formula and ideal vacuum using this formula, and then finally vacuum efficiency using this formula. That is actual vacuum divided by ideal vacuum. So this is about the vacuum efficiency. So in this we have covered two types of efficiencies related to the condensers. One is the condenser efficiency and another one is the vacuum efficiency. So now let's start with the steam turbines. Next topic. Just see this video and let's understand it. Okay, so these are the various objectives which we are going to cover in this video. Small video is there. So the first one is the view the history of steam turbines. Okay, what is the backend history of the steam turbine? Who is the inventor? Then classification of steam turbines. Then the study the working principle of impulse and reaction turbine, as there are different types of turbines, but we are going to study about these impulse and reaction turbines in this. Then specify the advantages and disadvantages of steam turbine. What are the various advantages and what are the various disadvantages of steam turbines? Then some of the applications related to the steam turbines. Now let's see the history of steam turbine. So this is the Sir Charles Anglo-Non-Parsons. He is the Anglo-Irish engineer who is the inventor of the steam turbine, and he invented it in the 1884. And the first steam turbine invented by him is of the capacity 7.5 kilowatt of electricity generation is there from that steam turbine. Okay, and as we know that steam turbines and electric generators work on the same shaft. They are assembled on the same shaft, and as the turbine rotates, the corresponding generator assembled on that shaft also starts rotating and generates electricity. Okay, so the speed of the turbine is related to the, and that means the generator speed depends upon the speed of the turbine. Okay, so he is the inventor behind the steam turbines. So this is the pic of the first model developed by Sir Charles. And now see the various classifications of steam turbines. The turbines in which thermal energy of steam is first converted into the kinetic energy and later converted into mechanical energy are called as steam turbines. That means the thermal energy of steam that is taken from the boilers is first converted into the kinetic energy. How this is converted into the kinetic energy? That is with the help of nozzles. Then later on, it is converted into the mechanical energy. Mechanical energy when the blades of the turbine starts rotating. So that is the steam turbines, definition for the steam turbine. Okay. So this is the pipe that is connected with the boiler, thermal energy. Then here it is a kinetic energy. And finally on the shaft, there comes to the mechanical energy. Now, there are two types of steam turbines. One is the impulse turbine and reaction turbine. See here, this is the impulse turbine and here it is the reaction turbine. And you have seen here that in the impulse turbine, this is the nozzle. Okay, here see the diameter is more as compared to the outlet diameter on the nozzle. Why this outlet diameter is very less? Because we want the steam outlet at very high velocity. So which is able to rotate these blades. These are the blades on the turbine wheels. These are the blades. But in case of the reaction turbine, so there are two types of blades. See here, there are two different colors of blades. One is having the blue color and other is having the red color. Okay, and also here the nozzle pipe is attached with the shaft also. Here in the impulse turbine, the nozzle pipe is not attached with this shaft. It is directly taken from the boiler side. But in case of this reaction turbine, the nozzle pipe is attached to the shaft. And in case of reaction turbine, when the shaft rotates, accordingly the nozzle also starts rotating with the shaft. And there are two different types of blades. Now let's see the impulse turbine first, the working of impulse turbine. Now see the diagram first. So these are the blades. These are the various casings. This is the nozzle. This is the runner. And these are the blades. Now this is the nozzle. And now see how the steam flows through the nozzle. Here the dia decreases and it is at very high velocity outlet. So that means the high pressure steam is converted into the kinetic energy. That means the velocity at the output of the nozzle increases to very high capacity. Velocity increases and this high velocity steam from the nozzle, that is called as the jet. And see here, this jet of steam is on when flows on the blades. So it tends to rotate these blades, And with this, the shaft and turbine runner rotates. And as this common shaft is connected to the generator also, and the generator also starts rotating and generates electricity. Now, these are the various characteristics related to this functioning of impulse turbine. So these are the characteristics, and these characteristics are based upon these two factors, like there is a nozzle stage and there is a blade stage. Okay, this is the nozzle stage, and see here in the nozzle stage, so this one is the pressure. This black dotted line, this represents your pressure. In the nozzle stage, the pressure decreases, and when the steam flows over the blades, the pressure remains constant. Okay, this is the curve for the pressure. With the nozzle, as the steam flowing through the nozzle, the pressure decreases and it remains constant when it flows to the moving blades. But in case of the velocity, so when the nozzle steam flows in the velocity starts increasing to the very high value, because with this high velocity, we can be able to rotate the blades of the turbine. But when this steam jet enters into the blades, the velocity starts decreasing. Okay, so this blue curve is for the velocity. And this is the velocity of the leaving steam. That is the velocity of the steam when it left the turbine and moved towards the condenser. Okay, and this is the velocity of the entering steam. This is the velocity of the entering steam, and this is the pressure of the leaving steam when it goes towards the condenser. Okay, so this is the characteristics related to the impulse turbine for pressure and velocity. Okay, this is the pressure of the leaving steam. This is the very high velocity, that is entering velocity of the steam. This is the velocity of the leaving. Now see for the reaction turbine. Now for the reaction turbine, as there are two types of blades. One is the fixed blades and another one is the moving blades. The fixed blades are directly attached with the casing. These are attached with the casing. Okay, and these are the moving blades that are not attached with this outer casing. And see here, the nozzle is directly attached to this shaft and it starts rotating. It rotates with the shaft. And this jet of steam, that is the steam flowing through the nozzle, is moved up upon the fixed blades. And when this steam enters to the moving blade starts rotating. Nozzle converts some part of the pressure energy into the kinetic energy because we want the steam at very high velocity here. So here also the shaft is connected with the generator. So see here the characteristics of the pressure and velocity. So see here, and what we observe here, that these are for the fixed blade, this is for moving blade, fixed blade and moving blade. So these are the various stages, and steam enters from the nozzle. Okay, when the steam enters from the nozzle, it is at high pressure. Okay, but when it moves towards the blades, it continuously decreasing. It decreases, then again decreases, and then it again decreases. Why it is decreasing? Because the steam expands into the when it flows over the turbine blades. So the pressure decreases with the expansion of the steam. But see here for the velocity, when the steam moves over the fixed blades, the velocity increases. But when it moves over the moving blades, the velocity decreases. Again, when the steam moves over the fixed blades, velocity increases. and then again decreases when it moves over the moving blades. Okay, and this is the velocity left for the leaving steam. The leaving steam that is then further fed to the condensers. Okay, and this is the pressure of the leaving steam. These two are for the condenser stage. Okay, and this is the velocity of the entering steam. Now see the comparison. See the comparison between the impulse turbine and the reaction turbine. Okay, see in the pressure for the impulse turbine, the pressure is decreasing, then remains constant. But in case of reaction turbine, the pressure is continuously decreasing until it leaves the turbine. Okay, and in case of velocity, when it is in the nozzle, it is increasing, and then decreasing velocity is there for the blades. But for the reaction turbine, for fixed blades, the velocity is increasing type, and for the moving blades, the velocity is decreasing type. See here. See the comparison of characteristics between the impulse turbine and the reaction turbine. Now the various advantages of steam turbines. It has immense load bearing capacity, highly reliable. The cost of maintenance and lubrication of the steam turbine is less. The steam turbine works with any type of boiler. Now the various disadvantages of steam turbines, like there is some specific amount of time required to start and stop the turbine. So this is a disadvantage. It also needs expensive high pressure boilers to produce steam. Now the various applications of steam turbines, that they are used in the steam power plants. This is the main application for the steam turbine. The different power plants, like in the thermal power plant, geothermal power plant, nuclear power plant, and solar power plant. Okay, so these are the various applications related to the steam turbines that they are used in the power plants mainly. Okay, so what we have covered in this complete video, that is first about their invention, then different types of steam turbine, then study their characteristics, then their advantages, then these disadvantages, and then the various applications related to the steam turbines. So from this video, we have seen the detailed functioning of the steam turbines related to the different types of steam turbines, their working, their characteristics, the pressure, velocity, advantages, disadvantages, and all that. Now let's see some theory part from this PDF also. That is the introduction to the steam turbines. A steam turbine is a device that converts the thermal energy of steam into the mechanical energy by turning the blades of rotor of the turbine. So see here the pic. So this is a pic of the actual turbine with having the arrangement of blades of different dia. Okay, see here the diameter is different. So the steam is allowed to flow over these blades with the help of nozzles. And as we have seen in the video also that, but it doesn't mean that there is a single nozzle coming from the boiler. Okay, there are different nozzles at different stages of the turbine. So this turbine consists of, actually in the actual power plants, so this turbine consists of different stages. Like here is the first stage, or here is the second stage or third stage, or they also named the different stages as low pressure stage, high pressure stage, or medium pressure stage. So there are different nozzles attached to the different stages. It doesn't mean that nozzle is only attached to starting. No, the nozzle is attached within the stages also. One nozzle is here, second nozzle is here, third is here, fourth one is here. So different nozzles are attached at the different stages of the turbines. which allows the jet of steam. Jet means the high velocity steam, which allows the jet of steam to flow over these blades. And with this high jet of steam, the blade starts rotating. Okay, and hence the thermal energy of steam is converted into the mechanical energy by turning the blades of rotor. Now the main application, as the prime movers in all the thermal and nuclear power plants to produce electricity. Okay, so these are the main prime mover for the generators. Okay, prime mover means that is a device for rotating a generator, a pre-device, because for the generator the rotation is required, and that rotation is given by these type of prime movers. We call them as the steam turbines. Okay, so these are used as a prime movers in thermal and nuclear power plant to produce electricity, and they are also used in the large ships, pumps and fans at petrochemical plants. Now the different classification of steam turbines, as we have seen already, that impulse turbine is there, reaction turbine is there, depending upon the behavior of the steam in the vicinity of the blades. So these are the impulse turbines and reaction turbine. So see here is the stationary nozzle. In case of impulse turbine, firstly from these two figures, in case of impulse turbine, there is the stationary nozzle that is directly taken from the boiler. But in case of the reaction turbine, the nozzle is attached with the rotating shaft of the turbine. And as the shaft rotates, the nozzle is also rotating along with that shaft. Okay, so this is the main difference between the impulse and reaction turbine. In impulse turbine, high velocity steam from the fixed nozzle impacts the blades, and this impulse drives the blades forward, causing the rotor to turn. Okay, so this high jet of steam allows the blade to move and the rotor rotates. The main feature of these turbine is that the heat drop per stage, as I have already told you, there are different stages. Okay, high pressure stage, low pressure stage and all that. So heat drop per stage can be quite large, allowing for large blades and a smaller number of stages. Okay, so in case of the impulse turbines, the number of stages are small, less, and the blades are of large size. The size of the blades is large, and also the heat drop per stage is also large. Okay, that's why the number of stages are less, so that there should not be so much of heat drop there. Okay, whereas in case of the reaction turbines, high velocity steam nozzles, steam from the nozzles striking the blades also produces impulse. See here, here it is the fixed nozzles are there, but here are the high velocity steam nozzles are there. But the steam jet runs into the blades, and the main force turning the rotor is the reactive force produced by the expansion of the steam flowing off the rotor blades themselves. So main force is here the reactive force that is due to the expansion of steam over the rotor blades. Because we know that in case of reaction turbine, the steam is continuously expanding within the different stages, and with that expansion of steam, the pressure is continuously decreasing in case of the reaction turbines. The main feature of this type of turbine is that in contrast to the impulse turbine, the heat drop per stage is less. So this is the main difference. Here the heat drop per stage is more, and here the heat drop per stage is less. So the blades become smaller and the number of stages increased. Okay, so these are the various differences in terms of construction, that here the blades, large blades are used, here the size of the blades are small blades are used. Okay, and here the number of stages are less, Why less? Because the heat drop is more, and here the number of stages are more because the heat drop is less. Okay, so this is the main difference between the impulse turbines and the reaction turbines. Okay, so this is all about today's lecture, and in today's lecture we have studied about the Dalton's pressure first, Dalton's law of partial pressure, which is discovered by the John Dalton, and then the different formulas related to the condenser efficiency, vacuum efficiency, then the effects of air leakage in the condensers. Then we study about the steam turbines, the different turbine types of turbines, their applications, their advantages and disadvantages. Okay, so this is all what we have covered in this lecture. Thank you.